It's been not given its proper due. I started doing it 30 years ago this year. And for many decades, it was treated as second-class citizens. Yeah. But now it is coming to the fore. It is ascendant. Okay. So, ladies and gentlemen, we have just gone and we have split up. We have split up here this data so that into two subsets, subset 1 and subset 2. And one of the questions which came from Kurt, I think, was the size of these subsets. And Kurt's premonition seems to have been correct. It's not a precise split, it's a probabilistic split, right? But a further question would be, what's the further question?
I mean, it's evenly dividable.
So these two are not chosen independently.
Right.
These two actually sum up to this. So it actually is splitting them between these. And even though you specify this fraction here, this fraction there, it's not that it independently peaks each. It actually is dividing them up. Okay? Okay, ladies and gentlemen. Okay. So having done that, let us train the model on a subset here, and then let us go and apply that on a different one. Okay. So here's a model trained on a subset. Okay, so we're going to train it. So what's going on here when we fit this? What do we have coming out of this? So we're fitting this thing called classifier here, and probably I chose a bad name for it. What is this thing? Well, this is something that knows,
I lost.
What is this classifier? This is something that knows how to estimate. It's an estimator. It knows how to estimate a model from this. Did something happen? Sorry, you were going to say?
I think Blinchiki has crashed or something. I don't know. I lost the connection to Blinchiki and then.
Oh gosh.
We're having problem with that.
Maybe it was huge.
Okay. Seems maybe it's intermittent. That one seemed to work okay. Okay, so I've just done this here. So what came out of this? Sorry? A model came out of it. So it estimated a model. Remember, this is an estimator. The model is a what? Transformer. This earlier vector assembler is a transformer. A transformer takes in a what? A data frame and returns a data frame. The estimator takes in a data frame and returns a what? A model. Returns a transformer.
Oh, I see.
Yeah. Okay, so I'm trying to convey to you some pieces of this. Okay. So here's a decision tree model trained on a subset. And now, ladies and gentlemen, trained on a subset, I would like to use that to, having produced that, I'd like to use it to transform this data, okay? So, ignore the code. The code I had a bug in it there. It said full data. This is what we want. We want to take this model trained on subset, decision tree model trained on subset 1, and we want to use it to transform the subset 2 of the data. Yeah. Do you see that? Okay. Next, what are we going to do? We're going to evaluate it. How are we going to apply it? How are we going to evaluate it?
Transform.
We're going to apply an evaluator. So in case you want to look at this, this is the decision tree model trained on subset 1. We're using it to transform the subset 2. Why? Well, we trained it on one subset. We trained it on one, now we're testing it on another. Having so done, we'll now use this classifier to evaluate. Now, if you didn't create the classifier, that's what this is, right? That's what this was. The binary classification, it's up here in the code I sent you. So in this evaluator, remember that it knows where to look for certain of its data to do its job. This is just like I was saying earlier. In ML library, you're often wiring these things up saying, okay, look here for your inputs, look here, put your outputs here. Here we are saying, look here for the label, here for the raw prediction made by the transformer. In other words, we're going to be using this data that was output here. It's going to have a raw prediction column, a label column. We're going to set the metric name area under ROC curve here, okay?
Why it's called binary?
Because it has
It's
to
a
do
multi-
with,
multi-
you're classifying, it's either true or false. So in this case, we are trying to classify, is it answered or not?
0 or 1.
0 or 1. Whereas if we were trying to classify, for example, will it be canceled? Will it be answered? Or will it expire? That wouldn't be amenable to an ROC curve, it turns out, just receiver operating. It's not just sensitivity to specificity, because you have more than 2 categories. Do you see what I'm saying?
So then we need to import the multi-classification evaluator or multinomial.
We would have, there's another evaluator that's I think it's called a more generic classification evaluator. But the binary one gives us access to certain results, okay, including this area under ROC curve. I think we may see the other classifier soon, okay? The other evaluator, yeah. Okay, so we created this binary classifier, or binary evaluator, and now we're going to evaluate this one we just created, this one that's trained on from a model trained on subset 1, and now it's applied to subset 2, excuse me. So here we are seeing that this evaluator is saying that basically the model that predicted subset 2, based on the model trained on subset 1 that predicted subset 2, has a area under the ROC curve of 0.735. Okay, and so that's indicating something about its sensitivity and specificity over different classifications. Now the interesting thing is you can go here and go look at the model. So this model that we applied, that we used to transform, this model that we estimated here.
Use the parameters.
Sorry?
It uses the parameters.
This indicates the decision rule it uses to classify. So it's saying feature 2, feature 0, feature 2, feature 0, feature 5. If this condition is met, predict 0. If this one is predict 0. Oh, most of them are predicting 0 right now. Later there'll be a predict 1. Okay, so this is actually giving an indication of the structure of this model.
But how does that make sense? If feature 5 is
Yeah,
less
no.
than or equal to 650, if it's greater than or equal to 65, also 0?
I think these are 2 mutually exclusive conditions,
But it's the same
but
number.
it's giving the same number, which
No, but the condition is
Confuses me,
the
yeah.
same number, 6, 5, 8,
Right.
3,
So if
7,
it's
0.
if this thing is less than A, do this. If it's greater than A, do that.
Do the same thing.
I know it's a weird thing that it's the same.
You should just pull that out and say predict 0.
Agreed.
Feature 5 doesn't make a difference.
Agreed. Let's try doing this with a smaller tree, shall we not? So how do we do it with a smaller tree, ladies and gentlemen? What would we need to do? Suppose we wanted to constrain it to be a smaller tree.
These would be options or whatever for the.
So what would we need to modify here?
Decision tree classifier.
Yeah. So one thing we could do here is, you notice we're only fitting this once. I mean, this decision tree classifier, we're fitting it actually here several times. So maybe we'll
Does it read to do it?
sorry.
Does it start again? Or does it add when you do the fitting?
I think it starts again. This is estimating de novo this series. So I'm going to say decision tree classifier shallow, all right? And we're going to here set. Note this decorator style. This is a very functional style of things where we're layering things onto this. Set max depth to what? 2. Let's say 2, okay? So let's say depth 2 instead of shallow. Let's say depth 2. What do you think?
Yeah. Think.
Good. By the way, is this imperative? It's actually creating a side effect? No, it's purely functional, ladies and gentlemen. Just because it has set, don't think it's imperative. It's not modifying state. It's just returning a value with that decoration on it, saying the max depth of this should be 2. Okay, so how are we going to train something? What do we do with this classifier? This is actually kind of a classifier factory. It's a classifier. It's an estimator for classifiers. Yeah, so we're going to fit the data. So let us apply ourselves now to this task. Shall we not? Okay. Okay. Decision tree classifier depth 2 dot fit. It's doing iterative operations here, ladies and gentlemen, in memory, circling over this data many times. And it's really valuable. The data can be cached for that it's stored in memory. Okay, so we've just trained it on that decision tree model depth 2. Let's go view it. How do I view it? Print debug string. Print debug string. There must be another. Oh, I thought it was print debug string. Is it to debug string? Sorry, not print to. There it is. There's our rule. Also doesn't look terribly efficient in terms of you would just think that both of these could be replaced by predict 0, right? But this is the rule here.
It's only using 2 features.
It's only using
3
2 features. Yeah, 3.
Well, it's not really using feature.
Oh, feature 0. Yeah, it's not. Yeah.
So
Okay.
the 6 features you gave it, it's only using 2.
That's right. So let's go see how it does. How are we going to evaluate it? Good. Iden, as normal, is one step ahead. Yeah. Okay, so let's try decision tree model depth 2. depth 2 trained on subset 1. And we're going to give it labeled subset 2 and depth 2. You don't have to use these long names if you don't want to. I have a secret feeling. I have a secret fear that maybe you folks are saying Val A equals this, Val B equals that.
The mathematicians use that all the time.
I know. And when I go to correct their code, I do so with a certain amount of
Right, but given that this
alacrity.
is functional,
Yeah.
based on math,
Yeah.
you know, they would have.
Fair enough. And I actually don't. I think that's reasonably the realm of argument. Yeah.
Yeah.
Um,
I don't know the clear answer to both. I just see
Yeah.
benefits.
Yeah, I could see benefits to both. It's nice if you at least use short names that somewhat indicate what you're dealing with. So X isn't sometimes an integer, sometimes a double, sometimes a model, sometimes an estimator, sometimes a evaluator. Yeah. Okay, and now let's evaluate it. So we can do so with the same evaluator. And we'll do so here. Okay, here we go. There's no state being updated, folks. It's beautiful. It's beautiful. 72%.
It's within 1% of the other one.
Pretty impressive, eh? Pretty impressive. A depth 2 tree is performing only slightly worse than a depth 5 tree. Okay, but our horizons end not there. That's a more poetic way of speaking. You shouldn't use in daily words, daily life. Let's now fit it on a different subset of data. Okay, let's try it on subset. Let's go fit to labeled subset 2. And we are going to use, let's use the depth 2 classifier. And this is going to yield a decision tree model, depth 2, trained on subset 2. Right? Do you see that? Okay. 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 What do we need to do to evaluate it? Transform. It's a transformer. A model is a transformer. What does a transformer operate upon? Upon what does a transformer operate? On a data set. So we just trained it on subset 2, so we're going to apply it to transform what? Subset 1. Okay. So it's a decision tree model trained on subset 2 that's predicting subset 1. Do you see that?
Now you evaluate it?
Now we evaluate it with our binary classification evaluator. Okay. There we go. $72.
73.
73%. It's actually pretty good evaluator. I mean, pretty good model coming out of that. Pretty good model. Let's try evaluating the full decision tree, the level 5 decision tree on this, right? Remember we had this level 5 decision tree? It was a 5-level decision tree before we transformed it. So let's go evaluate. Let's do the same thing. Decision tree model trained on subset 2. Okay? So I'm doing this here. You can copy it if you want from the corresponding thing here. We're going to train it on subset 2 of the data. See that? We're going to, well, first, before we train it, we have to create it. So we're going to estimate it from subset true. But what this classifier, what will be the depth of the tree that comes from this? Up to what? 5. How do we know that? Well, we could go look at the properties of the decision tree classifier. And probably it will end up taking considerably longer to estimate. So if you're not sure about what depth it is, this decision tree classifier, you could go and do decision tree classifier here. Decision tree classifier dot, is it max depth? Oh, that's the parameter. We'll get to that. Is it get max depth? Get max depth. Yeah, this is actually the parameter. It actually reifies the parameter, which will allow cross-validation to work. Because we're going to be able to tell the cross-validator, hey, vary this parameter. Ladies and gentlemen, here we are. We've trained it. So this is our model. What do we do to evaluate it? We need to transform, ladies and gentlemen. A model is a transformer. It's estimated by a classifier, which is an estimator, but the model itself is a transformer. So it's going to transform something for subset, we fitted it to subset
Trained on
subset 2. So we're going to give it subset 1 to evaluate, right? And here we are. DF predicted subset 1 from model trained on subset 2. So the depth of this tree is going to be up to what? 5, ladies and gentlemen. Here we go. So we fit it just a bit earlier. We fit it to subset 2, got back a tree. We had done it earlier. Does anyone remember to subset 1? What was the classifier? What was the accuracy of that one? Yeah, so the one when it was 73% with this deep tree. So we predicted subset 2 based on a model trained on subset 1. Let's go do it now. Okay, so how are we going to evaluate this now?
So is this the reverse of the previous one?
We're basically going through the same process for both a tree of depth 2.
But we did the depth 5 already. That's 73.5%.
For the first one. For now we're training it on subset 2 and we're evaluating its performance on subset 1. You ready? How are we going to evaluate it? Evaluator. Okay, here we are. Okay, so here we go. Oh! No, don't worry. Ready?
So
72%.
a little bit lower. It's lower than the 2-step one.
Exactly.
Does that make sense?
It's got a much bigger space, much higher dimensional space to search. So it actually may spend its time, it may not be able to find as good a tree. It's just got too big a search space. Imagine if I had to search, for a best solution on this table versus on this entire floor. It's actually possible I might be able to, and I only have, 1 minute to do it. I might actually be able to find a better solution here.
I think that's maybe overfitting.
Could be overfitting. It could be overfitting. Good
Because
point.
you have 5.
Good point. Good point. Excellent point. You could really be tuning the parameters very specifically to that
for
subset.
the set you're
Mm.
training.
Yeah, 'cause you're
But then
Good,
you
good
lose
call.
the
I
general.
think as normal, Winchell's wisdom is prescient. Okay, ladies and gentlemen. Next, let's go try one more classifier. Logistic regression we may have to leave till next time because it actually takes a little bit more time to estimate. Let's do a naive Bayes classifier. Okay? So the problem with the naive Bayes is that, ladies and gentlemen, it only will accept, gosh, I'm tempted to do logistic regression. Naive Bayes will only accept non-negative features. Okay? Maybe we'll do the logistic regression. So here you have the code before you. Let's go define that. So you note this, ladies and gentlemen, I tell you, for each session of this course, often it will take a day to prepare, and often that day is spent, 80% of it is like solving one, two, or three problems, specific problems that prevent getting there. Maybe it's not always a full day, but sometimes it is. And this was actually one that bit me. This was just not working. Logistic regression was just not working for me. I tried again and again and again. The problem was I was only using max iter like 1,000, and it was giving results that were, it doesn't converge. It doesn't converge. And so I ended up using a bunch of different ways, trying to figure out what was wrong. Is it something about the data format or something about the label or missing values? And I was really going around and around and creating very simple models and seeing our simple data sets. And finally, it turned out to be this issue of max iter. It actually needs to run for 100,000 iterations. Well, sorry. When I did it like 1,000, maybe even 10,000, it was not working. And I wasn't sure why it was until I tried it with 100,000 and it actually worked. Okay, so ladies and gentlemen, we just applied this, we fitted a logistic regression. So when I say logistic regression, it's a bad name on my part. I'm the first to admit my names are not great. Logistic regression, although they are long. Maybe that's why they're sometimes not great. Logistic regression is not itself a regression. What is this? It's an estimator to produce logistic regression models, right? So we just produced a model. It's an estimator. We produced it based on a data set. That's the job of estimators. Let's do subset 1 too, right? Let's do df label subset 1, and we'll make it trained on subset 1. Okay, here we go. Subset 1. Boom. Okay. Next, we are going to go look at the coefficients. This will allow us to take a look at the betas associated with the logistic regression. I think with confidence, I can trust that that's something to which Refot can relate. Because when you estimate with logistic regression, basically you're doing a fitting with a formulation that involves a number of betas corresponding to each of the features in the feature vector, right? So when we defined our feature vector, it consisted of several types of information. Remember that? Our feature vector up here, activity, orientation, gyroscope, x-axis orientation, y and z-axis. So here's the beta value for activity. Here's the beta value for orientation. Here's the beta value for gyroscope mag. And then these are beta values associated with each successive axis. Now, I don't want to submerge the fact that actually you may be able to get a certain amount of value out of changing the definition of the feature vector. Like maybe you don't want to use x-axis orientation by itself. Maybe you want to consider using its magnitude, for example. And that would be another thing to explore. But this gives you a hint as to the identity of that model. let's go more than that. This is a logistic regression. Let's go look at the objective history. It's been a while training this thing. What was it finding? Well, you'll notice it's pretty flat, actually. It got better and better, but only at very small levels, 0.675 down to 0.65. Makes you wonder, how good is the classification from it? It didn't actually get to a much, much better value. Shall we try it?
Didn't really converge.
From its kind of initial guess, it didn't really converge to a great value, even though we gave it latitude of 100,000 iterations. Let's do this. Let's evaluate it. Area under the ROC curve, 0.64. Is that less or better than the decision tree
Worse.
classifier? Worse. Indeed. Worse. Okay. So here we can actually with a logistic regression model, interestingly, you notice, you may have noticed something. I fitted it. I didn't even transform. It actually remembers its predictions for the thing on which it was trained. But let's go back to our logistic regression model trained on subset 1. Do you see that? What could we do if we want to now evaluate that in a more controlled way? This summary here is basically looking at how accurate this thing was during training. But that's not a very good way of judging it side by side with that earlier model. So let's go evaluate this in a more fair way, this logistic regression. What could we do to evaluate it, test it against a different subset? What do I need to do? We transform. A model is a transformer. A transformer takes in a what?
Data frame.
Okay, yeah, takes in a test. It takes in a testing data frame, exactly. So I'm actually going to do logistic regression model trained on a subset 1 of the data, and we're going to apply it to DF subset what?
Q.
Subset 2. And now let's evaluate it. Binary classification evaluator. I'm keenly aware of the time, and I want to free you. I know some of you have tight time between classes. Here we are. I'm just going to pass this directly on. This is going to yield a what? You have Dr. Stanley's class?
Yeah, we don't have that.
Oh.
Am I right?
Yeah, don't have it.
Okay,
Has
yeah.
to wait with meetings.
Yeah.
Meetings. Oh, okay. Oh, okay. Okay, that's good to know. Thanks for letting me know. Okay, ladies and gentlemen, here we're going to try it on, DF, what is it? Sorry. DF subset, I'm confused. It's DF labeled 2. A DF labeled subset 2. That's the name, right? %64% as well.
A little better, actually.
Slightly better. You notice what we've just done. We've just composed these two things. Once again, it brings out the functional nature of this. And in fact, if I really wanted to take that, fully without even naming things, what I could actually put in here is what? So if I wanted to transform subset 1 and evaluate that based on something that's trained on subset 2, what could I put in the middle there? Well, it would be logistic regression dot fit of what? Yeah. Here we go. Okay. And in fact, I don't even need these. these things, right? Okay, df labeled subset 2. What is this going to return?
Estimator.
A model. This is the estimator.
Oh, sorry.
Applying it to a data frame returns a model. Transforming that model, applying the model's transform on this is going to return a what?
Data frame.
Data frame, which we are going to then evaluate, right? This is functional, ladies and gentlemen. As befits its rightful place in that area of computation. Its rightful, at least, recognition. Okay. Here we go. Here we go. 63%. Okay. So it looks like logistic regression is underperforming when compared to a decision tree here. Naive Bayes classifier. Well, let's just finish with that. Here we need non-negative things. I'm tempted. Ooh. Yeah. Okay. Let's call discretion the better part of valor, and we'll stop for the day. Students are hungry, and professors are tired. So we'll stop for today. We'll continue on next time. Next time we're going to be continuing on to discuss a couple things. One thing is pipelines, cross-validation pipelines, where it'll automatically cross-validate the model by running it many times. Ladies and gentlemen, by doing this in a functional style, you can pass in an estimator as an object. It's reified as an object. And you can pass in parameters as objects. You can actually, a parameter is also an object. You can pass it into a cross-validator and basically say here, okay, with cross-validator, please go and modify this parameter, the reg parameter, to take on these potential values, and modify this parameter to take on these values, and use that for my cross-validator. And so here, I'm going to be able to create a cross-validator which uses a certain estimator, like a logistic regression estimator or a binary classifier estimator, sets an evaluator to judge it. You're telling it which things you wish to adjust and over what values you wish to adjust them. You're saying how many folds of the cross-validation to perform, 10-fold, 2-fold, 3-fold, and then, ladies and gentlemen, you can use that cross-validator to estimate a model. And like any other estimator, takes in a data frame and returns a model here, or these estimators. And then we can ask what's the best model and what's the objective history for that model. Okay?
And does it keep all the models?
That it considered? Or
Yeah, you're calling the best model here, but can we have a look on a few of them, for example?
it's a very good question. I don't know that off the top of my head, but we could find out for next time. Yeah, great question. Great question. Could you look at all the different, could you look at the second best, for example? See how better the one that it did get, to what degree was it privileged? To what degree was it head and shoulders above the others? Or to what degree is the runner-up just about as good? Yeah, so that's where we're going. We're also going to see multi-step data pipelines, ladies and gentlemen, when you're processing things like text data, which involve several stages of processing, even before they get to feature extraction. how those can be folded into pipelines. Ladies and gentlemen, this builds on, this helps capitalize on, this helps bring to its full potential some of the functional programming components of this. It's defined in a quite nice composable way, where you can compose these things together, you can combine them, and apply them in ways that are very modular and convenient. So the fact that we can substitute in our evaluator here, our logistic regression, the parameters that we wish to change, it's a mark of elegance reflecting its strong foundation. Okay? But that, ladies and gentlemen, is for next time. And I know many of you have a long road ahead before Tuesday for your other classes, and I'll look forward to working with you on that. Okay? Thank you.